Okay, hello friends, I am Rajneesh Kumar, working as assistant professor in NIT Pharmacy Institute. I am again in front of you with one more lecture. In the last lecture, we have discussed about the phenanthrene structure and the synthesis. Okay, so in this lecture, with the continuation of that previous lecture, we have discussed the reaction and the uses of the phenanthrene. Okay, so without any delay, I am just coming to the reactions part of the phenanthrene. So in the last lecture, we have also seen the structure of phenanthrene. So in the structure of phenanthrene, you can see that there is three benzene rings which are fused together in angular passions. Okay, so the 9 position like this. Okay, so numbering we have also discussed about that 4, 5, 6, 7, 8, 9 and 10. So this is the structure of phenanthrene, and we can also number that phenanthrene ring like this. So I have told you that the numbering should always started in the terminal benzene rings. We can start the numbering from this end, and we can also be start numbering from this end. Okay, we can also start numbering from this. Okay, so like this. So there is total 14 carbon, out of which 10 carbons will be numbered. Okay, so whenever a phenanthrene will go for the reaction, there is always a possibility that reaction will be done on 9 and 10th carbon. Okay, because that carbon are more reactive. So if we are talking about electrophilic substitution reaction, because it is having electron cloud above and below the plane of the phenanthrene, and it is a planar molecules. Because of that electron cloud, the most suitable reactions which phenanthrene can go is the electrophilic substitution reaction. Okay, so electrophilic substitution reaction, suppose we are going for the halogenation. Okay, so halogenation means we are treating this phenanthrene ring with the halogen and the presence of some Lewis acid. Okay, if we are not using Lewis acid, then electrophilic substitution reaction will not take place. Halogen will be added by addition reaction. Okay, so in the presence of some Lewis acid, we are going for the halogen. So on that type of reaction, that particular halogen will always be added on the 9th position. Okay, 9th position. Reduction and oxidation both can be takes part at 9 and 10 position, but monosubstitution in electrophilic substitution reaction will always take place at the 9th position. Okay, so again we know the mechanism of electrophilic substitution reaction. There is in the first step there is generation of electrophile. In the second step, then generation of intermediate carbocation, and in the third step removal of the proton from the ring. Okay, so again substitution will take place on which position will always depend on the stability of intermediate carbocation, which will be formed in between the electrophilic substitution reaction always. So on the basis of the stability of carbocation intermediate formed in the electrophilic substitution reaction, it is certain that reaction will always take place on 9 and 10 position. In case of di substitution, the first substitution will always take place at 9 position. Okay. So again if we are talking about a reduction, then it can phenanthrene actually can be reduced by the sodium and isoamyl alcohol or copper oxide and chromic acid, like you can see there, to 9,10 dihydrophenanthrene. Its oxidation with sodium dichromate and sulfuric acid yield 9,10 phenanthrene quinone. Yeah, as you can see there is oxidation occurring in the presence of sodium dichromate and sulfuric acid, and we are getting 9,10 phenanthroquinone as a product, while on reduction in the presence of sodium and isoamyl alcohol or copper oxide and chromic acid, we are getting 9,10 dihydrophenanthrene ring. So you can see that in case of reduction, this double bond will be broken, and the addition of 2 hydrogen will be occur at 9 and 10 position. In case of oxidation, 2 oxygen atoms will be added on the 9 and 10 position to get the oxidized product. Okay, now again when we are going for the addition of bromine, So again 9 and 10 position of the phenanthrene ring will be involved. So bromine by addition reaction mechanism will get 9,10 dibromophenanthrene as a product. Okay. When phenanthrene go for the ozonolysis in the presence of ozone and water, we are getting diphenic acid as a last product. Before that we are getting dialdehyde. Okay. That dialdehyde on again oxidation in the presence of very strong oxidizing agent like KMnO4 gives diphenic acid. Okay. So this is all about the reaction of phenanthrene in short. Then the most important part of the reaction of phenanthrene is electrophilic substitution reaction. Okay. So it also undergo electrophilic substitution because it is having electron cloud. It is also aromatic in nature. So it gives the same reaction like naphthalene or anthracene or benzene. Okay. So in case of electrophilic substitution reaction, the most important is Friedel-Crafts reaction. Okay. So the exception is there. Now, so previously I have said you that the 9 and 10 position are the most active position for giving the electrophilic substitution reaction in case of phenanthrene. But when phenanthrene undergoes Friedel-Crafts reaction, then substitution will always takes place at third position. It should be taken care of always. Okay. So again on nitration it gives 3 nitrophenanthrene and on bromination it gives 9 bromophenanthrene. So you can remember this point by remembering that only halogenation in electrophilic substitution reaction will take place at 9 position, while other like Friedel-Crafts reaction and nitration is taking place at the third position. Again, so here is the reaction. You can say there nitration it will take place in the presence of HNO3 and acetic anhydride. Okay, and we are getting 3 nitrophenanthrene as the main product. Okay, other substitution reaction substituted product can also be possible, but based on the stability, this 3 substituted nitro product is more stable. So this will be the major product. Okay, while in on bromination we are getting 9 substituted phenanthrene ring. So bromination, the mono substituted product, mono bromo substituted product phenanthrene will be formed, and again if we raise the temperature we can also substitute the 10th position of the phenanthrene, and we are getting disubstituted or dibromophenanthrene as a product. Okay. So the reaction of higher hydrocarbons with electrophilic reagents are more complex than that of naphthalene. So as you can see in the case of naphthalene, this is the formula of naphthalene. Okay. This is the formula of naphthalene. Okay. So there is alpha carbon, there is beta carbon, there is again you can say that this is beta carbon or gamma carbon and alpha carbon. Okay. So these 2 types of equivalent carbons are there in case of naphthalene, while if we are talking about the phenanthrene ring. Okay. So like this. Like this. Okay. Color is changed, doesn't matter. So here you can see there 1 2 3 4 5 6 7 8. So and 9 and 10. So if we go for the analysis, then we will found that 1 and 8 carbons are equivalent, 2 and 7 carbons are equivalent, 3 and 6 carbon are equivalent, and 4 and 5 carbons are equivalent. So this is so 1 8 it is called the alpha, 2 7 is the beta, 3 6 is the gamma, then 4, 5 is the delta. Okay, the 9 and 10th carbon are the equivalent, and those are the epsilons. Okay, so in case of naphthalene, only 2 types of equivalent carbons are there in the structure of naphthalene, while in case of phenanthrene, there is 5 types of equivalent carbons are there in the structure of phenanthrene. So the electrophilic substitution reaction in case of phenanthrene is little bit more complex when compared to the naphthalene. Okay, so for example, phenanthrene can be nitrated and sulfonated, and the product are mixture of 1, 2, 3 and 4 and 9 substituted phenanthrene. So substitution can be possible on all types of carbon. Okay, so total 5 types of carbons are there in case of phenanthrene. So substitution can be possible on all the carbons. Out of those 5 types of substitution reaction in case of phenanthrene, the major product will be the product which is having more stability. Okay, so however, the 9 and 10 bond in the phenanthrene is quite reactive. In fact, it is almost as reactive as an alkene double bond. So addition therefore occur fairly readily. Halogenation can give both 9, 10 addition and 9 substituted product. Okay, so if we go for the electrophilic substitution reaction mechanism, then we are getting 9 substituted product. Okay, if we change the temperature and the medium of the reactions, and we can also get di substituted product, di halo substituted products. Okay, so now we can also compare addition reaction as well as electrophilic substitution reaction in case of phenanthrene. So here, in case of electrophilic substitution reaction, we need some Lewis acid like AlCl3, FeBr3. Without the presence of Lewis acid, electrophilic substitution reaction will not take place, because in case of electrophilic substitution reaction, we need some what? Electrophile. Okay, electrophile. So for the generation of electrophile, we need FeBr3. Okay, so if we are not using FeBr3, then again we can get the disubstituted product, but this reaction will proceed through the addition reaction. Okay, the tendency for the phenanthrene to undergoes addition is due to the comparatively small sacrifice in resonance energy, that is approximately 20 kilocalorie per mole or less. Okay, so the habit of the phenanthrene to undergo addition reaction in place of electrophilic substitution reaction is the loss of very little amount of the resonance energy in that particular addition reaction. So because of that, phenanthrene will go for the addition reaction. Okay. Now the reactivity of 9 and 10 position towards electrophilic attack, whether reaction lead to the substitution or addition, is understandable, since the initially formed carbocation is the more stable. Again, I am telling you that there is the electrophilic substitution reaction is 3-step reaction. In first, generation of electrophile; in the second, formation or generation of carbocation; in the third, removal of the proton. Okay, so after the third step, we are getting our substituted products. So the reactivity of 9 and 10 position toward electrophilic attack, whether reaction lead to the substitution or addition, is unstable, since the initially formed carbocation is most stable one, in which aromatic substrate are preserved in 2 ring out of 3. Okay, so again we know that the stability of carbocation can be checked on the basis of certain parameters, like first of all we have seen we see that it is tertiary carbocation or secondary or primary. So all of you know that tertiary carbocation is more stable than the secondary than the primary. If all the resonating structure formed in between the electrophilic substitution reaction are same, means all are having tertiary carbocation or secondary carbocation or tertiary carbocation, then we go for checking another parameter, means we have to see that out of 3 ring of the phenanthrene, how much ring has having aromatic substrate intact. Okay, so suppose intermediate carbocation which is formed in electrophilic substitution reactions is having 5 resonating structure. Out of 5 resonating structure, in 3 structure, okay, in 3 structure, 2 benzene ring out of 3 is having aromatic structure intact. Means these particular structure will contribute more, okay, and the final reaction will be according to that particular stable carbocation structure. Okay. So this carbocation can either give a proton in the last step. Okay. So as soon as the proton will be removed from that carbocation, we are getting our substituted product, or it can also accept a nucleophile to yield the addition product. So again you have to take care of that the reaction addition as well as electrophilic substitution reaction is same, means both is having the formation of intermediate carbocation. In the last step, if it leave the proton, then reaction will go for electrophilic substitution reaction mechanism. If it will accept a nucleophile, then the reaction will go as per the addition reaction mechanism. Okay. Now there is a slide which is having reaction of phenanthrene in short. So as you can see that this phenanthrene molecule is there, it will reacted with the chlorine in the presence of carbon tetrachloride. So if carbon tetrachloride is there, it means it is not following the electrophilic substitution reaction, it is following the addition mechanism. Okay. Now in the next as a product we are getting monohalo substituted product, monochlorophenanthrene, or you can say 9-chlorophenanthrene. Okay. In the next reaction, when phenanthrene is reacted with the acetyl chloride in the presence of some Lewis acid like AlCl3, and we are getting 9-acetylated product. Okay. As a in the reaction. Okay. This is electrophilic substitution reaction. Then again in the presence of acetic anhydride, phenanthrene is reacted with the HNO3, concentrated HNO3, and we are getting 9-nitrophenanthrene ring, okay, which is not very stable actually. Okay. It is also having 1, 2, 3, yeah, nitro substituted. Okay. So this product is more stable than other. When phenanthrene is reacted with the concentrated SO4, again we are getting 3, actually this is SO3 3 substituted product. When it will react with the sodium metal in the presence of ethanol, we are getting reduced product. Okay. So you can see that there is 9,10 dihydrophenanthrene ring. Again when phenanthrene react with the chromate, okay, sodium dichromate, and the presence of concentrated SO4, we are getting 9,10 phenanthroquinone. Okay. So these are the summary of the reaction of the phenanthrene. Then the important part of the phenanthrene is its use, its application. So it's a very actually important chemical. So it's again very toxic also. It may produce cancer. So phenanthrene is a very important commercial chemical used as to make other chemicals, dyestuffs, drugs, and resins. It can also be used in biochemical research. Okay. So phenanthrene can produce phenanthraquinone, polyester, okay, resin, alkyl resins, benzene, anhydride, then ketohexamethyl. Then it can also be used in the preparation of anti-fogging agents of pulp. It can also be used in the synthesis of various alkaloids, and also it is it's a part of various natural alkaloids like morphine. Okay. In dyes industry, it can also be used in 2-amino phenanthroquinone, bendathrone, and sulfur vat dyes. So again it's a very important molecule. Okay. So as I told you that it is also having some toxic effects. Okay, so we have to take very much precautions while we are working on that particular molecule, that is phenanthrene. Okay, so whatever we use phenanthrene in their work, in research as well as in other work also. So they can breathe in vapors. They can breathe the phenanthrene in vapors, or they can also have direct skin contact with the phenanthrene. Okay, so the general population may be exposed by breathing in air actually. Okay, so again the cigarette smoke is also having phenanthrene. Okay, so general, if you are talking about general population, so they can breathe the phenanthrene in the air. They can also take phenanthrene by active or passive smoking cigarettes. They can also take phenanthrene by contacts with road dust and household dust consumptions of grilled or smoked food and contaminated fish or drink water. Okay, so if phenanthrene is released to the environment, suppose if phenanthrene is released to the environment, it will be broken down the air. It will be broken down in the air. Phenanthrene released in the air will be in or on particle that eventually fall to the ground. It is expected to be broken down by the sunlight. So if we can take the small precautions about the phenanthrene, then you can see that if sunlight is there and phenanthrene is present on the ground, then sunlight can destroy the phenanthrene ring, and it is not very much harmful for the human population. Okay, so as it, why? Because it will not move into air from the moist soil, okay, and water surface. It will be broken down by the microorganism also. Okay, and is not expected to build up in the some aquatic organism. So there is no need to worry about. Then there is a certain risk is there about the phenanthrene. Data on potential for the phenanthrene anolis to produce the toxic effect in human works are not available till now. Okay, it doesn't mean that we don't have the precautions. Data is not available, but certainly it is very toxic. It is carcinogenic. It can produce the cancer in in animals. Okay, so increased blood uric acid levels can also be associated with the phenanthrene exposure in coke. Even worker exposed to the maximum polynuclear aromatic hydrocarbon. This indicates a potential risk for kidney stones or gout with phenanthrene exposure. Based on data for the other polynuclear hydrocarbons, polynuclear aromatic hydrocarbons, irritation to skin, nose and throat may occur after touching or breathing phenanthrene. Okay, so increased sensitivity to sunlight and or skin allergic reactions may also occur following the skin exposure. So this is all about the phenanthrene, and the hope you have enjoyed the lecture. If you can see this lecture on the YouTube channels, and I will be there. If you have some questions about any topics, you can put in the comment box on YouTube channels. I will be certainly reply on that. So thank you so much.